Okay, perfect. I'll go ahead and get started then. So thanks so much for hosting me. I'm Sam. I'm the co-founder and CTO of Miston Labs and the creator of Move. And today I'm going to give a brief introduction to Move and specifically to the dialect of Move that we're using inside of Sui. So the outline of my talk today starts with the Move part, and a lot of this is motivation, trying to justify why crypto needs a new programming language, and in particular, why the kind of new programming language it needs has to be a safe language that's oriented around programming with assets. Then I'll talk about how in Sui we're combining Move with a new object-centric data model for transactions that makes a lot of common things that you want to do in blockchains easier and faster. So smart contract, let me just come out and Sui are always talking to builders and companies for hesitating or deciding not to jump in is basically that they're afraid of this. If you look at this thing on the left, this is one of my favorite websites, rec.news, and this is a leaderboard of all of the biggest money hacks that they've had. And it seems like every time I look at it, this list gets longer and longer and the numbers get bigger and bigger. And we're to the point now where a smart contract hack that steals tens of millions of dollars is basically a weekly occurrence. It's very mundane. No one is surprised at all. I think a lot of the stories that people tell about why this happens have to do with developers not being careful enough. You know, they're trying to make a quick buck or they're cowboys. But my experience in talking to smart contract developers is that they're extremely careful, they're extremely security conscious, and they really take their responsibility seriously. And so I actually don't think there's any reason to expect that future smart contract developers can do better with the same tooling. I think if anything, they'll probably be worse because they'll just be more focused on product development rather than being blockchain experts. So this means that in order to get beyond the status quo, to make crypto grow, to grow the pool of developers, and to reduce the hacks, we really need the languages and the tooling to improve significantly. I think safer languages and then building advanced testing and verification tools that sit on top of these languages are really going to be the only way to grow the crypto dev community in a sustainable way. So when we look at smart contracts, they're really quite unconventional programs, and I'm talking about what they are, so we can think about what the ideal smart contract language look like. I claim if you look at a smart contract, it's really only doing three different kinds of things. It's going to define new flavors of assets. It's going to have logic for reading some assets, writing them, perhaps transferring them between addresses. And then it's going to check access control policies to make sure that the sender of a transaction has the permission to touch these particular assets or to update them in certain ways. And so if this is really all smart contracts do, then that sort of tells us what we need from a language that's designed for programming the smart contracts. We need language support for safe abstractions, for defining your own custom assets, for writing, for having notions of ownership, for setting access control policies. And then from the safety perspective, we need language support for strong isolation. We need to be able to write safe open source code that interacts directly with untrusted code written by motivated attackers who really want to steal millions of your dollars. And not these aren't at all common tasks in conventional languages. We're usually not writing code that manages money or works with assets. And if we're worried about attackers getting at our code, we put it behind a firewall or run it in a separate process, which aren't options that are available to us in the smart contract setting. I claim also that existing smart contract languages do not support either of these tasks well. We see all the hacks that lead to security issues, and let me talk a little bit more about why these languages aren't very asset centric. So if you look at any other smart contract language, you typically can't do any of the following things. You can't pass an asset as an argument to a function. You can't return an asset from a function. You can't store it inside a data structure like a list or a map. You can't call a function and say, hey, I'd like you to temporarily borrow this asset, but please give it back to me when you're done. You can't declare an asset type inside contract one that ends up being reused by contract two, which really makes it difficult to write complex piece of code that build on what some previous piece of code has done. And then finally, you can't even take an asset outside of the contract that created it. The typical data model for assets and other smart contract languages is you have a hash table where the keys are addresses and the values are integers corresponding to balances or to the bytes of an NFT. And if you want to interact with those assets, you have to interact with its contract and call its functions. And there's just no way to ever take it outside or wrap it in another asset. I mean, you can implement these things, but you must do it in a very indirect way. So I claim that assets and ownership are the fundamental building blocks of smart contracts, but in existing languages, there's no vocabulary for describing them. And this leads to code that's very indirect, code that's hard to secure, code that just, frankly, isn't very fun to write either. And so with Move, we're really trying to tackle this problem head on. We want to provide the right abstractions for programming with assets so programmers can write what they're trying to say, what they're trying to say in a way that's very direct and very secure. So the way we do this is we encode assets and ownerships in the type system. In particular, they're encoded in Rust-like linear types with ownership and mutability and sharing right there in the types. So if you look at a piece of Move code like buy that takes a coin type as input and returns a car title, you should read this code as saying, if you give me being the function buy, a coin, then I will give you back a car title. And then so let's look at some other function. It's saying register. This one takes a reference to a car title and takes a coin and then gives back a car registration. And we should read this as saying, if you show me your car title and you pay me a fee, then I'm going to give you back a car registration. So this is a much more direct way of expressing it. Like, I'm not even showing you the code, but just from reading the types, you can tell what this function is going to do, and it can only be implemented basically in a way that does that. And something that we really want here is, of course, like car titles and car registrations and coins aren't going to be built into the language. We want these to be user-defined types that can be declared in different modules that the original author didn't necessarily anticipate interacting with. And we want the types to be able to flow across trust boundaries without losing integrity, and to be able to be embedded inside each other and to be mixed and matched in arbitrary ways while always maintaining safety. And so the way we do this is in the type system, we have protections that prevent common kinds of misuses of asset values. So the first very important one is duplication. So like, let's look at this example function f. It takes a coin as input. If I was going to write some code that said, let x equals c, in an ordinary language, what that's doing is that's going to copy c or whatever the thing on the right-hand side is. But of course, if c is supposed to be a coin, that's not going to be acceptable. I shouldn't be able to get more coins just by copying the bytes in some variable. So the type system in Move is going to prevent you from doing this. And similarly, if you take a reference to C, let y equals ampersand C, and then you're going to dereference it, that's also a form of copying. And so that has to be illegal as well. Also, double spending. If you're going to be using coins as payment, let's say this function h takes a coin as input, and then it calls some function called pay and passes C into it, then I better not be able to call pay again in the same function or even use C after it's gone into pay. In both of those cases, the type system should give me an error and stop me from doing it. Then finally, destruction. If you're going to store coins and assets and NFTs and program variables, you want to make sure that you don't accidentally destroy them or drop them on the floor. So this function takes a coin as input, and then if you do something like try to overwrite that variable C, you'd be destroying the coin that used to be stored in C. So the type system needs to throw an error here. Or similarly, let's say you take a coin as input and then you return without using it. Also, the type system should say, hey, you're accidentally letting this go out of scope. You need to move C, pass it to a function, put it in global storage, send it to an address, do something before the end of this function. So really, what this type system is doing is taking a setting where there's no inherent scarcity, inside the computer, everything is just bytes, and it's trying to give you a notion of scarcity, a nice abstraction, digital assets that behave exactly like physical ones. And the way we actually let programmers do this is quite flexible. I didn't show you how coin was implemented, but what we would do is we would say struct coin, and then we would choose which abilities we're going to give to this coin type. And so there are 4 different ones, and let me explain what each of them means. And a struct doesn't have to have one ability, they can be mixed and matched arbitrarily. So the first one is copy, and this basically says something's allowed to be duplicated. It has memcopy. So if you're defining something like a string, like of course you want to allow it to be copied. So this is useful. But if you don't give your struct the copy ability, then the only way to create one of these things is explicitly via the constructor in the module that declares the type. So if you're declaring a coin, like you would not want to give it copy, for example. Similarly, there's this drop ability. A drop allows you to discard a type without calling an explicit destructor. You just let it go out of scope, you overwrite the variable, and all of these sorts of things. And if you don't give something the drop ability, then it ensures that the struct can only be eliminated by an explicit call to the destructor. So if you're trying to have something like a coin or NFT, you don't want to give it copy and drop, but common types like strings and all of these things, like of course they're going to have both the copy and the drop ability. Move also has built-in global storage. This is representing the coins or NFTs or assets in your accounts. And you can have abilities that tell you whether a type is allowed to appear in global storage or not, and where in global storage it's allowed to appear. So this struct k has key. This says that it's allowed to appear in sort of the top level of global storage. You can look up this object by its ID or by its type. Um, then there's the store ability that says, okay, it's not a key. You can't look it up directly in global storage, but I can put it in the fields of other objects that have the store or the key ability. And then there's this interesting trick that you can do by giving a struct no abilities. If it doesn't have drop and it doesn't have key or store, then there's no way to get rid of it except for calling the destructor. So it means that it needs to die inside the same transaction that created it. And so this is a cool trick that you can use for implementing something like a flash loan. You give someone a hot potato that says how much they need to pay back, and then the only way they can get rid of it is calling a function inside your flash loan contract that actually pays back the loan plus the interest and fee. So this has been about the expressivity and asset-centric part. Let's move on to talking a little bit about the safety features for Move. Move is, in the design of the language, we've really optimized for safety and for predictability and for amenability to static analysis and formal verification. So the first thing is that we don't have any dynamic dispatch, no interfaces in the language. Every time you look at a call site, it's monomorphic. You know exactly what can be called statically without running the code. And this in turn implies that there's no reentrancy, which is of course a very common attack vector in conventional smart contract languages. Very much like Rust, we have both aliasing and mutability, but we don't allow you to mix them. So whenever you don't get confused about the value of some code changing whenever you have a mutation, things are very predictable in that way. The type safety, memory safety, and then the resource safety related to the ability system I described on the previous slide, they're all enforced not only by the compiler, but also by a bytecode verifier that runs before you publish any code on chain. So if an attacker is trying to trick the type system and write some code that copies your assets or violates memory safety or does something nasty, that'll be caught by the bytecode verifier. And this is what allows us to have types that flow across trust boundaries without losing their integrity. There are strong isolation features, including this nifty security property called robust safety that are built into the language. Basically, like you write your code inside a module and you enforce some invariants on it, and then the language guarantees that no matter what attacker code interacts with it, if you make those invariants hold locally, then they're also going to hold globally for any possible attacker code. And then finally, and this is a small thing, but these things matter. Things like integer overflow or division by zero or common, not unexpected overflow or division by zero are common sources of problems in other smart contract languages. So in Move, anything that's mathematically ill-defined aborts by default. If you create an integer overflow by accident, your code just aborts. It doesn't, accidentally do the wrong thing. And if you're familiar with Solidity, it's sort of like everything. It's safe math by default instead of having to import that. And then let me talk a little bit about the Move Prover formal verification tool, which is something we've developed alongside the language that helps you specify application-specific properties that matter for your program, and then check that they hold for all possible transactions, for all possible inputs, for all possible program invocations, which is the most powerful form of correctness guarantees that you can get. So this thing has a specification language where you can say something like, the total supply of my coin should match the number of coins in existence, or only the admin should be able to access this NFT mint or things like that. This language is integrated with the compiler, so you can write your specs, the compiler just understands them, and then the prover is integrated with the Move CLI, so you can type move run, move build, and move test, and move run, but you can also just type move prove and run the prover quite directly. A lot of formal verification tools are slow and unstable, but the prover is very fast and very stable. You can run it locally, you can run it in CI, and we often do have it turned on in CI for both the Move repo itself and for the blockchains that are using Move. And finally, we use the prover heavily inside the Move standard library. We specify and verify all the key properties that we care about. And we've tried hard to make the prover accessible so that you don't have to be an expert in formal verification or a Move core contributor to know how to use it. And there's some evidence that we've been successful in this. Like here's a recent pull request where someone added a bunch of helper functions to a math library in the standard library. This person isn't a Sui developer or Move core contributor. They're just sort of a random community member. And in the test plan, you see they say, okay, I kept the test coverage at 100% and I added new Move specs, which are verified. So this is quite cool because formal verification is often only accessible to experts, but here we see community contributors, just coming in and sending a random PR, and they're able to use this verification feature, which is quite nifty. And finally, Move has been designed to be platform agnostic. the status quo with existing smart contract languages is basically like every new blockchain has its own language, or it looks substantially like the previous blockchain that the language was initially designed for. So, and this is because these languages don't try very hard to keep platform specific features out. They tend to hard code design decisions like the account format, the transaction format, what serialization scheme you're using, what cryptography you're using, even details of the consensus like the block structure. And so what this means is that if you want to use the language in a new platform, like say I want to write some new EVM compatible platform, I'm going to have to inherit a lot of the design decisions and a lot of the limitations of a theory program. Whereas I might want to strike out and do something new and more scalable and more interesting. So in Move, we've tried really hard to keep all these things out of the language, where in particular, it's agnostic to all of the features above. And this allows designers to experiment with different choices for each of these. And from the programmer perspective, blockchain, you can learn Move and you can reuse your expertise, the tooling, the libraries across all of the different platforms that integrate Move. And so things are very early on, but so far Move is already used in 5 different blockchains that look very, very different from each other under the hood, and have different approaches to transactions and parallelization and scaling. So there's the original DM, there's Sui, there's Aptos, there's OL, there's Starcoin, and we're seeing lots of interest from existing blockchains for adding Move as a second language that they support, or emerging blockchains that are trying to pick their smart contract language, and they're taking a hard look at Move. So the vision we have for Move is really that it's the sort of WASM of Web3, just like you have WASM running everywhere in the background. We think if you interact with assets, if you interact with smart contracts, you really want to be good in Move, and you want the Move VM to be running and security and keeping everything safe. So that's the end of the going to talk briefly about Sui Move and just some additions and improvements we've made to the core language as it was originally designed for DM. So the code on this slide is some code that I think is not the best code but is the only way to write something in the original DM style of Move. And then I'll show you how we've improved this in Sui Move. And so what we're trying to do here is very simple. We have an NFT and we just want to write some logic that lets you transfer this NFT, but in the lock period, we don't want you to sell it for the first 30 days until 30 days after you initially buy it. Say to prevent speculation. And so I don't necessarily want you to look at this code closely, but I want you to notice how many you have to define a table that holds multiple NFTs of the same type. This is because in DM style Move, the structure of the global storage requires you to have at most one value of a given type under an address. So if you want to have multiple of these NFTs, you have to define a table so you know how to have different ones to pick them out by their ID. The second thing is that in DM style Move, you can't just transfer an asset to an address. The asset has to opt in to the permission to receiving that asset. So first they have to send a transaction that publishes one of these tables into their account. And now they're ready to receive this asset if someone sends it to them. And then let's look at the actual function for transferring, which, although it's doing something simple, is quite long. First, what you do is you take in the address of the person who you're sending to, and you grab the table out from under their address and you pull it out, and then you remove the asset from the sender. And then finally in step 4 here, you actually do the interesting thing of checking this lockup period. And then step 5 is sort of step 3 in reverse. You look up the same table on the recipient side, you put the asset into it, and then you finally give it to them. And so this is quite cumbersome for doing something very simple and quite common in smart contracts. And really, when we were designing Sui, we look at this, and the problem is that although Move is asset centric, when I call table remove here, I actually have an asset in a program variable. The API with transactions and with the global storage are not very asset centric at all, which leads me to have to write all this boilerplate. And so what I really want as a programmer is to be able to pass this cool asset NFT directly into the cool transfer function and then transfer it directly to the recipient, and then not have to do all of these annoying steps in between. And so here's the same code in Sui Move. It's quite simple. You see you have cool transfer. It takes asset directly as an input, and then it checks the lockup period. This part is quite simple. You just look at the date and add 30 days, and then you transfer it directly to the recipient. In Sui Move, sorry, does someone have a question? Okay, I'll continue. In SwiMove, there's a generic transfer function that can transfer any object without having to pre-publish a table or to send something else. And so you don't need to, then the reason for this is that Sui addresses distinguish objects by ID rather than by type. So every address can automatically receive all the types that are there, and there's no pre-publishing or setup that needs to be done. And then the reason you can pass in cool asset directly to cool transfer instead of writing this code to look it up and remove it is that the Sui runtime does this for you. And it's because the asset has ownership metadata built into it. And let me explain how that part works. So in SwiMove, the structure of the global storage and the system is fully asset centric. The global storage is organized as a map from an object ID to an object, and all objects have stable and globally unique IDs. One way to think about this might be that everything is an NFT, and all of these objects have common ownership metadata that's checked by the runtime, which saves programmers from forgetting to check authentication, which is a very common source of bugs in other languages. And then what this lets us do is to have a transaction data model that has this common vocabulary for expressing inputs and outputs. All transaction inputs and outputs are expressed in terms of objects. So like, in this transaction here, it says, hey, I'm taking this object ID A as input and this object ID B, and then I'm going to mutate the object ID A and have it at some new version. I'll delete ID B and I'll create this new object ID C. And so we can see that when we look at a transaction, it's easy to describe what it does without running it just in terms of these objects. And its dependencies are explicit and statically known, which I don't have time to cover in detail in this talk, but makes it a lot easier to do parallel execution and parallel sequencing and many of the high performance tricks that Sui is doing to squeeze out. So let me dive into the ownership metadata and then I'll wrap up. So the ownership metadata moves a lot of common authentication checks and smart contract languages into the runtime. And so what the data looks like is you can say an object O is owned by some address A, in which case only a transaction signed by A can use O. It can be owned by another object P, which means any transaction that also includes P can look O up at runtime, or it can be shared, which means that anyone can use O. And this is the way that you would represent an auction or a DEX or some object that multiple writers can access at the same time. Then in a transaction, you have an entry function, which is the logic of the actual transaction. And it includes types that are just these Rust style ownership types. If you ask for a big T, it means that the function is asking for permission to transfer the object or to delete it and to write it and read it. If it asks for ampersand UT, it's asking for permission to write and read it. Whereas if it's asking for ampersand T, it's just asking for permission to read. So because of this ownership metadata, what the runtime does is it takes object IDs as input, and then it can download the objects, check that the sender owns it or that it's shared. It checks the object type against the entry function signature to make sure you're not passing in a coin where an NFT is expected. And then it calls the function with the object arguments. And this has a bunch of other beneficial effects too. I'll just mention one of them because I think it's interesting. A big problem with wallets is that in existing ecosystems is that you're being asked to sign something, but it's usually an opaque blob of bytes and you really don't know what it's going to do. But because the Sui transaction format tells you which objects it's going to use and what it's asking you to do with them, it can enable these very human readable, like sort of end user understandable Android or iOS style permission requests. And this is a lot simpler, cheaper than trying to run the transaction and see what happens. So just to give one very concrete example, like a common kind of scam is that someone will say, hey, if you have a Bored Ape, like this is a promotional giveaway, you get some other promotional NFT as part of it. And then the thing will actually steal your Bored Ape instead of giving you the promotional NFT. And so in SwiMove, this wouldn't work because your giveaway function, if it's safe, will only ask for permission to read your asset. And that's right there in the type signature. So your wallet can give you permission that says, hey, this app wants to read your cool asset. Is that okay? And you'll say, yes, that's safe. Nothing bad can come from just reading my asset. Whereas if it's something malicious that wants to steal your asset, it's going to need to ask for permission to transfer it. There won't be an ampersand here. And so your wallet can say, hey, this thing that's claiming to do a giveaway wants to transfer your asset. Are you okay with that? And you'll say, no, I don't think that makes sense. I only want to give permission to read here, just like you wouldn't approve an Android app that's asking for permission to record video when it is just sending text and that sort of thing. So um, this has been an overview of Move and a little bit of a window into to Sui Move that talks about how we marry this asset-centric programming language with a new transaction data model and all of the benefits that come from that. So the in a longer talk or in our docs, or if you look into Sui, I think this new data model is quite interesting and can be leveraged in a surprising number of ways. This more direct programming style, as I mentioned, for safer wallets, for maximizing parallelism in both TX sequencing and TX execution, and also for other things like scaling throughput and storage, and for discouraging contention with new schemes for pricing gas that's based on objects and how often they're touched. So I'll put a bunch of links to the move related resources and to Sui related resources below. And that's all I have to talk about today. But thank you so much for inviting me, and I'm happy to answer any questions you have.